Hello, Mr. Betts here. We're going to take a look at three fairly straightforward examples of using the second derivative test. Now, I want to point out that each of the problems that we're going to do here, we could find relative extrema using the first derivative test, but I want to focus on the second derivative test so that we get some practice using it. There will be some problems that you'll see where you will be forced to use a second derivative test based on the information that's given to you. But in these examples, we're going to use it just because the directions ask us to. So in order to use a second derivative test, there's two things that we're looking for finding relative extrema. The first is where the first derivative at some point is equal to zero. So we're looking for critical values, but specifically critical values where the derivative equals zero. And then we're going to look at the concavity at those points. So whether the second derivative is either positive or negative. And based on that information, we're going to be able to conclude that certain points are going to be relative maximums or relative minimums. So first thing we're going to do here is take the first derivative. So first derivative is going to be 6x squared minus 18x plus 12. And a common mistake with the second derivative test is to think that everything we're going to do has to do with the second derivative. Really, the first piece of information we need, though, is where the first derivative is equal to zero. So we're going to start there. We set that equal to zero. We can factor out a 6. And then we can factor that polynomial. And so we get critical values at x equals 2 and just put comma 1. Now, specifically, these critical values, again, are where the derivative is equal to 0, and that is necessary to use the second derivative test. Now, the second thing I'm looking for is what is the sign of the second derivative at those points. So to do that, we're going to have to take the second derivative, and then what we're going to do is we're going to plug in these two critical values that we got where the derivative was equal to 0. So we want to know what is the second derivative at 2. So we're going to have 12 times 2 is 24 minus 18 is 6. And the key here is that that is greater than 0, so that's positive. And then we also want to know what is the second derivative at 1. And if we plug 1 in, we have 12 minus 18, which is negative 6. And the key here is that that is negative or less than 0. So now we can answer the question. And the question says determine the x-coordinates of any relative extrema. So all I'm looking for here is the 2 and the 1. I might need to actually find the coordinates, so the y-coordinate also. You are not asked to do that here, so we don't have to plug it back into the original function. So the x-coordinates, and then classify it as a relative maximum or a relative minimum. And I'm actually going to do one more thing here and justify it. So justify why it is a relative minimum or relative maximum. So we'll say f has a relative, and let's just go in the order we have them here. So at x equals 2, we have a horizontal tangent, and it's going to be concave up. So horizontal tangent and concave up is going to give us a relative minimum at x equals 2. Because, so our justification with the second derivative test has to say that the first derivative at that point is equal to 0, and the second derivative at that point is positive. So we want to say first derivative is equal to 0, the second derivative is equal to whatever it is, and show that that's either positive or negative. And then the second one, we have f has a relative maximum at x equals 1 because f prime of 1 is equal to 0, so we have a horizontal tangent there, and the second derivative at 1 is negative 6, which is less than 0, so it's going to be concave down. So horizontal tangent, concave down, gives us a relative maximum at that point. Second problem here, another polynomial. This one's pretty straightforward. So we are going to start with the first derivative. We're going to set that first derivative equal to 0. We can factor out a 20x cubed, and then we get x minus 1 left over. So we get critical values where the derivative equals 0 at x equals 0 and x equals 1. Now we want to evaluate the second derivative at those points. So we'll take the second derivative first. So that's going to be 80x cubed minus 60x squared. And then we're going to evaluate that second derivative at our two critical values. So the second derivative evaluated at 0 is going to be 0 minus 0, which is 0. And the second derivative evaluated at 1 is going to be 80 minus 60, which is positive 20. So we have a point here where we actually don't have enough information to conclude whether it's a relative minimum or relative maximum. So what we have here at x equals 0 is a horizontal tangent, but then the curvature, the concavity, doesn't tell us if it's concave up or concave down, and in fact, it's neither at the point. I'm going to show you a graph of this in a minute, but what's happening here is this function is behaving essentially like a straight line really close to the point, and then it starts curving away from the point. So it looks like any other curve that would have it turns out in this one, a relative maximum, but the curvature right around the point is really close to 0. So it's behaving more like a straight line. So we cannot make a conclusion at this point using the second derivative test. We could go back and use the first derivative test at this point because we can look at the signs of the first derivative to the left and to the right of 0, and that would give us a relative extreme at that point. At this one, at x equals 1, this is going to be, since the second derivative is positive, it's concave up, so this is going to be a relative minimum. And so we'll say g has a relative minimum at x equals 1 because g prime of 1 is equal to 0, and g double prime of 1 is 20, which is positive. So again, my justification for the second derivative test always includes the first derivative equals 0, and then the value of the second derivative, and then indicate whether that's positive or negative. If we look at the graph of this, you can see that the graph of this function does flatten out and looks pretty much like a straight line. So the concavity at this point itself is actually 0. So a concavity of 0 means that the function is a straight line. And at that point, this function really is behaving like a straight line. So the first derivative test, that would actually help us here because the first derivative would be, this is g, the first derivative is positive everywhere to the left, and it is positive at least in the vicinity immediately to the right. So where the derivative changes from positive to negative, we are going to get a relative maximum at that point. Okay, last example. And this example is just a matter of going through the same steps we have on the last couple. So we want to take the first derivative. We're going to have to use the product rule here. So derivative of the first times the second plus the first times the derivative of the second. We're going to set that equal to 0, and we factor. So we can factor out an x and an e to the x, and then what's left here is going to be 2 plus x. So we get critical values, again, specifically critical values where the derivative equals 0. That is important with the second derivative test. We don't want the critical values where the derivative is undefined. And we get critical values at x equals 0, and we get a critical value at x equals negative 2. So for the second derivative test, we want to plug those values into the second derivative. So to take the second derivative, this is going to be fun. I think probably this form right here would be easiest because if we take the derivative of this form, we're going to have to use the product rule 2 times. So we're going to have to use the product rule twice anyway, but we'll do it with the separate terms instead of 3 factors. So anyway, product rule on the 2x times e to the x. So derivative of the first times the second plus the first times the derivative of the second. And then product rule on the second term, we have derivative of the first times the second plus the first times the derivative of the second. And I'm going to simplify that. I'm going to start simplifying by factoring the e to the x out. And then we're going to have x squared plus 4x plus 2 left inside. We don't need to set this equal to 0. And indeed, this expression right here, we'd have to use the quadratic formula because that doesn't factor, but that's okay. So we want to know what is the second derivative evaluated at each of these points. So we're going to have e to the 0 times 2. Remember, e is positive, so this is 2e. E is positive, so this is positive. And the second derivative evaluated at negative 2. So we have e to the negative 2 times negative 2 squared is 4, minus 8 is negative 4, plus 2 is negative 2. So this is going to be negative 2 over e squared, and that's going to be a negative number. So based on that information, where the second derivative is positive, the function is going to be concave up, and therefore we're going to have a relative minimum. And then where the function is concave down, we're going to have a relative maximum. So h has a relative, let's do the minimum first, at x equals 0, because h prime of 0 equals 0, and h double prime of 0 is 2e, which is positive. Then we can say h has a relative maximum at x equals negative 2, because h prime of negative 2 equals 0, and h double prime of negative 2 is equal to negative 2 over e squared, which is negative. The form that you write this expression right here doesn't matter. You could have left it like this and just say that's negative. That would have been okay. But you do need to evaluate it to actually show that it is negative at that point.